All right, welcome back. So today we are going to delve into the second fundamental theorem of integral calculus. Sort of naturally follows from the first, as one might expect. But to sort of set the stage for this articulation, let me just remind us that previously, when we were trying to develop an exact estimate, well, maybe it's not an estimate if it's exact, an exact value for the signed area between a function's graph and the horizontal axis on an interval AB, we observed that if little f has an antiderivative, we could use the mean value theorem and get that the definite integral from a to b of our function, the exact area, the exact signed area between the function's graph and the horizontal axis, is just capital F of b minus capital F of a, where, of course, here capital F is just our antiderivative function. Last time, when we developed the first fundamental theorem, we made an observation about accumulation functions. So accumulation functions are sort of describing the area that accumulates, the signed area that accumulates between a function's graph and the horizontal axis on an interval of interest. And well, if a function f of t is continuous on AB, then the accumulation function describing its signed area from a to x has a first derivative, a prime of x, equal to f of x. Important to note, last time we discussed, I failed to include or really highlight the continuity assumption that is associated with this idea. That is an important thing. Ultimately, whenever we determined that as h gets close to 0, the function is only changing so much in value, that actually relates to the fact that the function were continuous. If the function were not continuous, the function's values could be jumping all around. The fact that the function is continuous means that the function's values are only changing so much, and as a result, we computed the area of such a thin rectangle, and then ultimately the h is canceled in our derivative expression, and we got down to the first derivative of our accumulation function being just f of x. But now, what does this all say? Because if we take these two ideas here that are sketched out on the board, and we sort of think about the logical consequences therein, some really nice things occur. So, well, think about this first fundamental theorem, because I claim that something follows from the first fundamental theorem. So let me write up here consequences. Well, we assume that function little f was continuous, and when we looked at the accumulation function, we found a function capital A whose derivative was little f. But wait a second. If we found a function whose derivative is little f, then we found a function that is an antiderivative of little f. So consequences here, one of the consequences is that if f is continuous, its accumulation function, a of x, this is integral from a to x of f of t dt, is an antiderivative of little f. So what's kind of beautiful about this idea is that assuming, the only assumption we have, if f is continuous, assuming you have a continuous function, then you have an antiderivative via the accumulation function. So hey, what this is saying is essentially, in other words, let me write it in this form. In other words, all continuous functions have antiderivatives. And that is a non-trivial idea, right? Because when it comes to first semester calculus, Math 141, continuous functions were not necessarily differentiable, right? You have the classic case of like the absolute value v, where you have a function which you can sketch without picking up your pencil. It's a continuous function, but it is a function, the absolute value function, that is not differentiable, namely at the corner located at x equals 0. So not all continuous functions are differentiable. However, via accumulation functions, all continuous functions are anti-differentiable. So that's a pretty cool idea, I suppose. Sort of suggests something that's at least very nice about antiderivatives. Whereas derivatives sort of had the challenge of all continuous functions not being differentiable, antiderivatives do not have that same challenge. All continuous functions have antiderivatives. But now, if we know that all continuous functions have antiderivatives, let's take this and reflect back upon that fact that we developed from the mean value theorem a few weeks ago, or well, at least a few meetings ago, which turns out maybe it's a couple weeks ago, but however long ago it was, we developed this idea that assuming little f has an antiderivative, then we get this integral from a to b of f of x dx, this definite integral, evaluating to be capital F of b minus capital F of a. We have to have an antiderivative for this to hold. But we just showed via the first fundamental theorem that all continuous functions have antiderivatives. So having an antiderivative can essentially just be thought of as a consequence of being continuous. And so what we can say is then if function f is continuous on AB, well then it has an antiderivative via its accumulation function, which means our fact about the mean value theorem would apply. Then we could say the integral from a to b of f of x dx is just capital F of b minus capital F of a. And as it turns out, this statement here, going off of the continuity assumption rather than the existence of an antiderivative assumption, is what is normally referred to as the second fundamental theorem of integral calculus. And so what we should take away essentially from the second fundamental theorem is we are phrasing a result that we previously saw via the mean value theorem using accumulation functions now simply as a consequence of continuity. So whether or not a function has an antiderivative can really be thought of as just a function of continuity, which is quite nice because when you think about functions that are continuous, actually it's kind of hard to think about a function that's not. You're going to have to come up with some sort of piecewise function with a jump or something like this. But when it comes to a sine function or a parabola or a line or whatever it may be, polynomial functions in general, trig functions in general, exponential functions, logarithmic functions, these are all continuous functions. So basically every function that you dealt with back in Calc 1, where you had to be sensitive to the fact that continuity may not lead to differentiability, here in Calc 2, we don't have to be sensitive to that fact at all. Continuity necessarily implies an antiderivative existing, which necessarily implies that once you have that antiderivative, you can compute the signed area between that function's graph and the horizontal axis lickety-split, capital F of b minus capital F of a, which is, if you recall back to whenever we developed it, an amazing fact, because we had this gigantic summation which simplified so much as it did. And now, hey, any continuous function we are dealing with, we can go compute the signed area between that function's graph and the horizontal axis via an antiderivative function, and we know that antiderivative function is out there somewhere because every continuous function has an antiderivative thanks to the first fundamental theorem. So not too shabby for a week or a couple weeks work. We've gotten ourselves to a really nice framework where we can sort of play integral calculus with a lot more fervor because, well, we don't have to be as hesitant about how to deal with such functions, as provided you have continuity, integrate away.